hello. All right, everyone, let's get started. Welcome back from spring break. It was a little bit longer than we expected, so I hope we're all rejuvenated and ready to go. As you could tell, I'm not Professor Fireman. My name is Jackie Capron. I'm Ellen Fireman's head teaching assistant, and she has trusted me to teach you about normal approximation today, so I think that we're going to have a lot of fun together. So let's dive right in and talk about where we left off before spring break. Ellen Fireman was talking about the central limit theorem. And so let's shake off the rust a little bit and think about what that means. That means if we're dealing with a random chance process, you know, like drawing tickets from a box, if we're dealing with a truly random process, the greater the number of draws, the more our probability histogram is going to grow to shape like the beautiful normal curve that we've become so familiar with. Now, why is this useful? This is going to be useful for us. It's going to make our lives a lot easier because instead of having to make painstaking probability histograms for each problem, like you spent time doing last Thursday, your Thursday before break with Professor Fireman, where you were drawing the probability histogram of flipping a coin 3 times. Well, for 3 times, that took us like 5 minutes. Can you imagine how it would be if we were going to do this for long problems where we were concerned with drawing 100 times from a box? So it's going to make our lives a lot easier. We don't have to worry about drawing these probability histograms anymore because the more and more times we draw from this box, no matter how lopsided the box is, the more it's going to look like the normal curve. So I could talk till I'm blue, but nothing will demonstrate this to you like an illustration. So I'm going to go over to our box model program. So let's imagine we were going to roll a die, and are you guys able to see this? Yeah, oh, there we go. So let's imagine that we were going to roll a die and we were going to sum up the total number of spots, for let's say 100 rolls. And we were concerned in what the total sum of the spots would be. So if you have, I think we're familiar with this, we've been using it for our homework. So let's say we have one ticket that says 1, we got one ticket that says 2, a ticket that says 3, ticket that says 4, ticket that says 5, and one that says 6, just like a die. So let's take a look at our box. There we go, we have 6 equally likely options. Now before I go on, the idea of a box model has been confusing some students in my office hours. What the heck is this box model? What are these tickets? What is this all about? Well, a box model, we're literally talking about a box with tickets in it. How many of you, when you were younger, were making a decision with your friends on what to do and somebody said flip a coin and everybody reached into their pockets and nobody had a coin? What do you do next? You grab a piece of paper, you rip it up, there's the heads, there's the tails, you roll them up, throw them into a box in whichever one, that's the decision that's being made. You just made an ad hoc box model. You were able to simulate the probability of flipping a coin by using tickets. So this is all we're talking about. So instead of having a bunch of statisticians sitting in a dark room flipping one coin all day, it's much easier to generate the same probability while using these box models. And in the age of computers, this has become much more easy. Instead of having a shoebox up here with 6 tickets, I'm able to just plug these numbers into the computer. So it's very handy. So that's what we're talking about when we're talking about these box models. So here's my box. I've got 6 equally likely options. So let's accept this box and make our histogram of the sums. So now watch what happens. Here's my box right now. Here's the probability on one pull. I'm equally likely to pull a 1, 2, 3, 4, 5, and 6. So now let's see. When I start drawing from the box, look it, on already even just 6 draws, this thing is starting to get pretty normal, right? Starting to look like this beautiful normal curve that we're so familiar with. Isn't that just amazing? Just 50 draws, 60 draws, it just becomes more and more normal. Now you guys are saying, well, Jackie, you're tricking us because this box was equally likely. Well, let's try this again with a lopsided box. Let's do it, instead of just dealing with a die, let's make it a really weird die. Instead of having one ticket that says 6, let's make it 300. So that's not like our usual die at all, right? Look at how lopsided that is. We are way more likely to pull a 6 out than any of the others. Let's experiment with this. All right, so let's start doing this. Wow, okay, definitely not looking like the normal curve. Not looking like the normal curve, but wait. What? Statistics magic. What is this? It is looking like the normal curve. Now you'll notice, look, we're down to about 326 draws, still going, and now it's starting to look really normal. Have I blown your minds just now? Is this amazing or what? It's so beautiful. So you'll notice the first box I did where I had 6 equally likely draws, where that was a very balanced box, I was able to reach that normal curve very rapidly, right? We were able to get that beautiful curve with only, 50 draws or so. This one with this lopsided box, we're over 500 and we're starting to look normal. So the moral of the story, the main point I want to get across here is that the more lopsided your box, the more abnormal, unusual your box is, the longer it's going to take, the more draws it's going to take for our probability histogram to reach that beautiful normal curve. So, everybody with me so far? Let's jump back over onto our document camera right here. Go back to our work. So, this is where we left off before break. So now let's take a look at this example. See if I can stop throwing things around. Okay, so let's look at the probability histogram for the sum of 25 and 50 draws. So 2 different amounts of draws. One that's 25, one that's 50 from box A and B. Let's look at box A first. We got 1, 2, and 3. This is similar to the die situation that I was just doing, where we've got a very beautifully balanced box. We've got 1 ticket for each number, and they're all right directly in a row. So this is going to look, if I were going to draw this box model, it would be nice and balanced. 1, 2, 3, equally likely for each. Now this box, box B, is lopsided, right? We've got 1 and 2, but then way down over there, are you able to see that? Yep, there you go. You got 1, 2, and 9. So this is very lopsided. So which box do you think we're going to be able to reach the normal curve faster with, A or B? A. A is normal. We're going to be able to reach that normal curve much more easily than we will with this lopsided. So we're going to say this is a balanced box, and we're going to say that this is a lopsided box. And look at these illustrations are exactly what I was just showing you on the overhead. Here is this beautiful normal box, only 25 draws, and look at how normal it is already. Beautiful, right? And then with 50 draws, it's even better. So that's how this normal, beautiful, balanced box works. And if you can see, I know it's kind of hard up here on the overhead, but if you look in your own box, what do these numbers say up here? It says the average for the sum of the draws is 50. And what do we see right here? Boom, 50, right in the center of our probability histogram. So that center number is basically our expected value for the sum of the draws on 25 draws. And what's this? The SD, so this is basically our standard error for the sum of the draws, 4.082, right? So that's just what those numbers mean, because you're going to be seeing that in your homework and probably on exams too. So then let's look over here. The expected value for the 25 draw, or the 50 draws, which is much more balanced, is 100. And there we go, our beautiful, beautiful balanced box. But now with box B, here we are with 25 draws. It's looking symmetrical, but it's a little bit choppy, right? So we still need to make some more draws to get normal. And then there we are over here at 50, definitely looking more normal, but we still have a ways to go. And just reiterating up here, the average of this box was 2, and the average of this box was 4. And if you weren't convinced when I told you that this was our expected value of 50 down here, let's try and figure out how we would do that. The expected value of the sum is n times the average. Well, what was our n in this scenario? 25. And what was our average? 2. 25 times 2, boom, 50. Point proven, right? So if we could do that for each one, and you'll see that as long as you can calculate the average of the box, which is very easy to do, that you can figure out the expected value for each of these probability histograms. And we could calculate the standard deviation for each of these boxes too, and I could prove to you that the standard error is that way as well. So, should we move on to an example? So, example 5. 25 draws are made with replacement from the boxes below. So we've got box A with 1, 0, and 1, 1. So that's what I would call a very balanced box, an equal number of tickets for two numbers that are directly next to each other on the number line. Now this one's got 9 zeros and 1 1. That's looking a little bit lopsided, right? And then, wow, over here, box C, we've got 24 zeros and 1 1. So this one is very, very lopsided. We'd say this is a lopsided box. Very lopsided. While this side is more balanced. So again, which of these boxes is going to take the most draws to get normal? A, B, or C? What do you guys think? C. C is going to take the longest. We're going to have to do the most draws to get there. So now let's take a look down here. So we're doing 25 draws with replacement from the boxes. So now we're going to draw the same number of times from each of these boxes. Let's see, box or histogram, probability histogram 1. What do you think? That's kind of normal, right? Got a little bit of a right-hand tail. This one is very normal, a little choppy still, and this one has got some work to do, right? So if we were going to look, the most normal curve, this one is the most normal curve. Which box do you think this one came from? Box A, B, or C? Probably A, exactly. Now let's go over here to the other extreme. Good test-taking strategy, start with your extremes. This one is the least normal. This is very lopsided. So let's say we're going to say this is the least normal. And so which box did this one come from? C, exactly. This one is very lopsided. See, we have so many more zeros than we do ones. That's why we see the bulk of this histogram very low and just a little bit of a tail where we were pulling out those ones, those lucky ones. So that's why this histogram looks the way it does. So process of elimination, we would say that this one has got to be box B, right? And that makes sense. It is, you know, an intermediate of the two, right? So, move on to example 6. Am I totally putting you guys to sleep yet? Should I wake you up with an eye clicker? All right. This is going to be exciting. Get ready. So, example 6. This is exactly the example in your book as well. Histogram 1 is the sum of how many draws from the box. So remember, what I want you guys to be thinking about when you're doing this problem is it to get that normal curve, do we have to do more draws or less draws? Think about that while you're doing this problem. So you're going to have to be looking in your book real fast. So we've got below are the probability histograms for the sum of 100, 400, and 900 draws from a box that has 99 tickets marked 0 and 1 ticket marked 1. So real fast, I'm just going to run back over to the document camera just to give you guys an indication of what the probability of one draw from this looks like. So we've got 99 zeros. Okay, so that's going to be like, there we go, those 99 zeros, and then just one tiny little 1. So there it is. You would definitely want to be betting on 0, right? We have way more zeros. So here are 3 curves. One of these curves is pulling 100 times from this box, one of them is 400 times from this box, and one of them is 900 times from this box. So let's go back over here and get that eye clicker rolling. Okay, so this is the question we're going to be dealing with. Oh, you guys can't see yet. So this is the question we're going to be dealing with. Histogram 1. Do we think that this is going to be 100 draws, 400 draws, or 900 draws? So let's start polling. And this one shouldn't take you too long. So ask yourself, is histogram 1 a normal looking curve, or is it kind of a choppy looking curve? All right, and I'll let you guys get up to 30 seconds before I stop you. Get those votes in. Everybody good? Last chance? Okay. All right, now let's look at our results. Great, you guys are doing awesome. So 85% of you guys think that histogram 1 has got to be A, 100 draws from this box. So let's run back over to the document camera. And you guys are right. Look at histogram 1. This thing is very abnormal, right? So we know this is going to be the fewest amount of draws from this box. So we're going to say that N is 100 because this is an oh, I'm sorry, guys. I'm going on without me. There you go. Can you see? There we go. That is quite a transition. Oh, I'm scaring myself right now. I doing something wrong? Okay. Oh, no. Don't move. Okay. Should I move? I'm scared to move. Oh. Okay, let's see. Yes, all right, we're back in business, folks. Okay, so histogram 1, it's abnormal, right? This is an abnormal shape, right? It's not the normal curve. So we're going to say this is going to be the least number of draws. And histogram 3, we would say what? This has got to be the most draws, right? So this has got to be n equals 900, because this is a very normal looking curve. So what's our intermediate here? We're going to say this is n equals 400, where we're getting there, but we still need some more draws to get to that normal curve. So any questions on this? Is everybody feeling all right on this? Let's move on. We got a lot of material to cover. So now this is my favorite topic in statistics. We are going on to normal approximation. So normal approximation is taking advantage of this central limit theorem and saying we no longer need to draw these probability histograms for each individual problem that we do. We can just use the normal curve to figure out the likelihood of a certain event occurring. So if anybody was in Vegas this past week, I'm sorry I didn't give you the lecture earlier, because this really comes in handy when you're figuring out the probability of winning when you're gambling. And we're going to get onto that later, so for all you gamblers out there. So let's see, the normal approximation amounts to taking advantage of the central limit theorem. We replace the true probability histogram for the sum, or average, or percent of the draws by the normal curve before computing areas. So you can use the normal curve to calculate the chance sum of a number of draws made at random with replacement. At random is key. These are random events. These are chance events, all right? With replacement from a box falls in a given range. So how do we do this? So convert to standard units. This is just like the #1 golden rule in statistics. Convert to standard units using the EV for the average and the SE for the SD. So this is nothing new, right? Remember what we were doing before? How did we used to convert to a z-score? What was our old z formula? Value minus average over standard deviation. So that's like so exam 1, right? We're moving on now. We have a new z-score formula. We're saying that now, when we're dealing with these probability histograms with normal approximation, z is equal to the value minus the expected value over the standard error. So this is our new best friend right here. Great. Okay. So no better way to illustrate this than with an example. So example 7a, in 100 coin tosses, what is the chance of getting less than 45 heads? So we're flipping a coin 100 times, and we want to find the probability that we get less than 45 heads, 45 or under, right? So let's hit this. All right, so since there are 100 draws, we know that the probability histogram will be very close to that normal curve. So we can use that instead of having to sit here for another half hour generating our own probability histogram. So we've got a step-by-step process. So let's get rolling. Step 1, draw the box model for tossing a fair coin. All right, so here's our little shoebox that I'm drawing. And we know there are 2 events that could happen when you toss a fair coin, right? You could either get your heads, you could get your tails. But we're not really concerned with, the letters here, what a head stands for, what a tail stands for. We're just going to consider head is what we're looking for. So anytime we're deciding what we're looking for, we're always going to signify that with a 1, because we're summing up the number of heads we're seeing. So each time we pull a 1 from that box, we're going to say, or every time we pull a head, flip a coin and get a head, we're going to say, yes, that's 1 head, 2 heads, 3 heads, 4 heads. So we're basically tailing them up. So we're going to say heads is 1, and what's tails? We don't care about tails, because we're only worried about getting our heads. So tails, every time we get a tail, we're just going to move on. Don't count anything. And there's only 1 of each, right? So there's our histogram, there's our box model. All right, so step 2, so step 1 done. Step 2, find the expected value and the standard error for the sum. All right, so expected value of the sum. Here's another formula for you guys. Let's see, we have expected value is n times the average, right? And what's n? N is given to us, right? They told us 100 draws, so there is our n. And what's the average? Well, we first have to compute that, so let's just go over here The average of this box. Well, we've got one ticket that says 1, and we got one ticket that says 0, over how many tickets total? 2. So that gets us an average of 1/2. So back over here, our expected value of the sum is going to be 100 times 1/2, so 100 times 0.5. And that gets us an expected value of 50. Now, that was a lot of numbers for something that you guys could have already told me, right? Flip a coin 100 times, how many heads do you expect to get? 50. You didn't do any math in your head, right? That's just your instinct, your intuition, right? But here's the math behind it, all right? So let's go on to the standard error. So the standard error of the sum, and the formula for that is the standard deviation times the square root of n. So square root of n, that's the easy part. We know we have 100 draws, but this SD we need to calculate as well. And luckily there's only 2 types of tickets in the box, so we can use our shortcut formula. So we're going to take the absolute value of what the tickets say on them, so we got tickets that say 1 and 0, times the square root of the fraction of tickets. So we've got 2 tickets total. We got 1 ticket that says 1, 1 ticket that says 0. So our standard deviation is also 1/2. Okay, so there we go. So we're going to do 0.5 times the square root of 100. And that is going to get us 5. Anybody lost? This is all stuff you've done before, right? Okay, so step 2, complete. So step 3, this is new. Well, not really though. We know this too. Convert the value, 45 heads, to a z-score and find the appropriate area on the normal curve. So let's go back to our new best friend, our z-score formula. Z is equal to the value minus the expected value over the standard error. And the part that everybody gets hung up on is, what the heck is this value? Well, go back to what the problem's asking us. They're concerned with the probability of getting less than 45 heads. That's the number of interest, right? So that is going to be our value. So 45 heads. So we're concerned with the probability of getting 45 heads. And what was our expected value for 100 tosses? 50. And divide by our standard error, which we said was 5. So we're going to get a z-score of -1. Great, so now let's move on to our normal curve. So we have a beautiful normal curve right here. Are you guys able to see me all right? Okay, so here we got 0 in the middle, z-score of 1, 2, 3, -1, -2, -3. And these are all of the z-scores, right? Now if we wanted to make another axis down below it in terms of heads, your expected value always goes right in the middle. So we would say that we would always expect to get 50 heads. And then we're going to break those up into intervals of 5, because that's what our standard error is. So there's 55, there's 60, 65, go the other way. Great, so now we have 2 axes, just so you know that these numbers are not just coming out of thin air, right? And these are the number of heads. Okay, so our z-score is -1, so boom, there we are. That is the point at which there are 45 heads. Now what's the rule that we do? Every time you plot one z-score, you always have to plot its opposite evil twin, right? So there's -1, there's 1. Okay, so what is the middle area? And if anybody's flipping to the back of the book, shame on you, because we should all have this committed to memory right now. We know that the middle area for a z-score of 1 is 68%. So 100 minus 68 divided by 2, we know we're going to have a tail of 16 over here, 16 over here. Now, we've done all the math, all the hard work is done. We have everything that we need to answer this question, and this is the point I see on exams where students go totally wrong. The answer is in front of you. It's a matter of reading the data, interpreting the data. So go back to what the question's asking us. They're concerned with the probability of getting less than 45 heads. And remember, here we are right here, -1, 45 heads. This is us on a little road map. So what's less than 45 heads? This direction, right? So all we're doing is we're going to be concerned with the probability, the area of this little segment of our normal curve. So let's make a little conclusion over here so we know what all this hard work was for. Our conclusion. So when we flip a coin 100 times, there is a 16% chance that we will get less than 45 heads. Boom. So there's the answer to the problem, and there's why we did it, right? That's the whole point. So if one of your friends was going to bet you, hey, let's flip a coin, you know, if you're really bored on a Friday, I guess, well, let's flip a coin 100 times, and I'll bet you $20 you get less than 45. You know, you have a 16% chance, so that's not terrible, but I wouldn't take that bet. I'd probably get some new friends, too. All right, so here we are. Next, moving on. Okay, so another example. So what is in 100 tosses, what's the chance of getting between 40 and 60% heads? Now there's two things you should notice that's different about this than the last problem. First of all, these percent signs are blaring out at us, right? So we're no longer dealing with the sum, we're concerned with the percent. The other thing is, we've been given a range of numbers, right? So we're not just concerned with one corner of the graph, right? We're going to be concerned with the area between 2 points on the normal curve. So back to step 1, draw the box for tossing a fair coin. So this is going to be the exact same box as before. We got one ticket that says 1, one ticket that says 0 to represent one head and one tail. Great, step 1, we're flying. Step 2, expected value and standard error for the percent of heads in 100 tosses from the box. So let's start here. Go back to our formulas, right? The expected value for the percent. What's the formula for the expected value for the percent? There is none, right? There's no formula. This is just common sense, right? So the expected value for the percent of our draws is going to be equal to the expected value of the actual box. Like if I had a big bag of gold up here and I said that there's 90% gold and 10% fake gold, I don't know, fool's gold, and you came up here and you picked out 100 nuggets, what would you expect to get? 90% of your little sample would be gold, just because it came from the bag of gold, the bag that had 90% gold. So our sample is always going to be reflecting our box for percentage. So if we have a box that has, what percentage of this box has heads in it? Well, we've got one, we got one head out of the 2 tickets. So we got 1 out of the 2 tickets. So that means we've got 50% heads in our box. So our expected value of the percent is also 50%, right? Does that make sense? So no formula there, just a little bit of common sense. Okay. So the standard error for the tosses. Now there's a formula for this one, so let's see. Standard error for the percent is going to be the standard deviation divided by the square root of n times 100. Okay, so let's see. We need to find our SD, but we know the square root of n is the square root of 100 times 100, so there's just kind of the bare bones. So let's go over here and figure out the standard deviation. So the standard deviation of this box, again, is going to be, we have one ticket that says 1, we got tickets that say 1 and 0, and out of the 2 tickets, one of them says 1, one of them says 0, so again, our standard deviation is 0.5. So back over here, fill in that blank, just so you know where that came from. Okay, and so that is going to get us what? 5%. So there's our expected value of 50%. There's our standard error of 5%. Everybody with me so far? Same process as before, we're just dealing with percents now. Okay, so now, step 2, done, boom. Step 3, convert the values. And what are the values again? Those are the numbers of interest. We were concerned with getting between 40 and 60 heads, so our values are going to be 40 and 60. To z-scores and find the area of the interval on the normal curve. So let's start with this 40, okay? So z-score is equal to value minus expected value over standard error. Am I going too quickly? Yes or no? No? Okay, just shout out, anybody, shout out if you need me to slow down, repeat anything. I know I'm a quick talker. Slow me down, all right? So here's our z-score formula, same as before. Our first value, let's start with the lower one first. Our first value of interest is that 40% heads. Well, what percentage of heads did we expect to get? We expected to get 50% heads because our box had 50% heads. And our standard error is going to be 5% heads. So that's going to get us negative 10 divided by 5, which is going to get us negative 2. So there's our first z-score. Great. Let's move on to our second z-score. So now let's think about this 60%. So again, same process. 60% is our value of interest. We expected to get 50%. Divided by that standard error of 5% gets us 10 over 5, gets us positive 2. So our two z-scores are negative 2 and positive 2. So let's go over down here. Here's our beautiful normal curve. Negative 1, negative 2, negative 3. There we go. And remember, those are the z-scores. And if we were to draw another axis down here below with the percent of heads, what would we see right here in the center under a z-score of 0? 50. It's our expected value. And we're going to go in intervals of 5 because our standard error is 5. So there's 55%, there's 45%. And I'll go down another one, 40%, 60%. So without even doing any math, we know we're concerned in the area between 40 and 60%. The area between negative 2 and 2. That's our area of interest. So let's plot those z-scores. There's negative 2 for our 40%. There's positive 2 for our 60%. And what's the middle area for that? 95. Always 95. Another one that should be committed to memory. But you know where to find it if you forgot. Okay, so 95% middle area. So 100 minus the 95 divided 2 ways is going to get us 2.5% here. 2.5% here. Again, all our work is done. The hard part is over. It's just interpreting the data. We're concerned in the chance that we get between these two percentages. Well, between these two z-scores, what do we see? 95%. So there is our probability. So, again, for a little conclusion, just to wrap things up on this one. Conclusion, in 100 tosses, let's see, we will get between 40 and 60% heads 95% of the time. Not exactly literary genius right there, but gets the point across, right? Okay, any questions on that example? Same thing we were just doing before. Now we're just working with percentages. All right, let's keep chugging. Okay, so now this should look familiar. This is straight from chapter 14. We're just going to add a little bit more to it now that we're learning some more. So, 36 draws are made at random with replacement with a box containing 4 tickets. We got a 0, a 2, a 2, and an 8. So you'd expect the sum of the 36 draws to be blank, give or take blank. So whenever you see this, you'd expect the sum. What is that? That sounds like, that's like our best bet, right? Our best bet in the 36 draws would be blank. So this is our expected value, right? And give or take, what does give or take mean? It's like the wiggle room, right? It's like give or take that amount, a little bit of wiggle room, and that is always going to be our standard error. So give or take some level of error. Okay, so first we need to fill in this first blank with our expected value and the second blank with our standard error. So we're going to use the expected value of the sum first, which we said was n times the average. What's our n? Always given to us, 36. What's our average of the box? Oh, let's get back here and do some work then. So the average of this box, did I go off screen? No, I'm all right. Average of this box, 0 plus 2 plus 2 plus 8 divided by 4 tickets is 3. So 36 times 3. And what is that? 108, right? Okay, so we would expect to see 108 as our sum, okay? Give or take, so now we got to go to our standard error. So standard error of the sum is going to be the SD times the square root of n. Now, can we use our shortcut formula for the SD here? No, because we have more than 2 types of tickets. We've got 0s, 2s, and 8s. So we got to go back to what we learned before. And let's just do a quick little refresher there. If we were going to figure out the SD, we got 0, 2, 2, and 8. If we wanted to figure out the standard deviation, and this is just, I don't know, I don't want to say never, but I don't expect that you'll have to do this on the exam, but you will have to do it on the final. So a good thing to pay attention to. So step 1 is find the average of the box, which we said was 3. So step 2 is take the deviations from average. So we've got a ticket that says 0, 2, 2, and 8. Deviations from average is how far away they are from that average of 3. So we're going to subtract 3 from each of them. So we're going to get -3 here, we're going to get -1 here, -1 here, 5 here. Then step 3, put it over here, we got to square them. So I'm going to square this guy, square this guy, square this guy. Is this totally forgotten, or is this ringing some bells? Silence is not a good sign. Okay, so you square your deviations from average, and then step 4, you take the average of your squares. So we're going to take the average of 9 and 1 and 1 and 25, divided 4 ways, and get 9. And last but not least, you got to take your square root. So the square root of 9 is 3. Boom! Aren't you guys glad that we learned the shortcut? That would get exhausting every time. So the long story short, the standard deviation of this problem is 3. So we have our average, and the SD of this box is 3. So if you have any questions about that or want a refresher, you can always go back in your notes and of course ask me questions. Stop by office hours. Okay. So back to where we were. We're trying to find the standard error of the sum. So the standard deviation we said was 3. And the square root of n, square root of the 36, right? So that's going to get us 3 times 6, which is 18. So there we are. We would expect to see a sum of 108, give or take the standard error of 18. So now that's all, we've done that before, that's nothing new, right? So now step 2, the second part of the question is, what is the chance that the sum of the 36 draws will be greater than 120? So here's the new concept that we're thinking about. So what's the first step? We don't have the steps lined out in front of us anymore. What's the first thing? The first rule of statistics, always go to standard units. So we're going to make this into a z-score. Value minus expected value over the standard error. And what is our value? What's our number of interest? 120. We're concerned with getting greater than 120. And what did we expect to get? 108. And divide by that standard error of 18. So we're going to get, what, 12 over 18, and that's like 2/3, so we'll say 0.67. So that is our z-score, positive 0.67, okay? So next step, let's head over to our normal curve. There's 0, 1, 2, 3. Okay, there's our normal curve. So where's 0.67 on here? 2/3 of the way between 0 and 1. There we are. That's 0.67. Okay, and what's the rule? Whenever you plot one, you always have to plot the other. So let's go over to our other guy, our negative 0.67, negative 0.67. That's who that is. Okay, oh, that did not turn out good, did it? Oh, try and balance that a little more. So what's the area between those two z-scores? Well, that one I don't even have memorized, so let's go to the back of the book then, figure out the area between 0.67 and negative 0.67. So our z-score is 0.67. Oh, we got 0.65 and 0.7. So it's going to be between those z-scores, which means our middle area is going to be between these two areas, between 48 and 52. So what do you guys say? We'll call it 50? Call it 50. And people always ask me, they freak out during exams. They say, oh, I don't see the perfect area on the chart. What should my middle area be? Just give it your best shot, you know? Just find the kind of the average between those two numbers. We wouldn't mark you wrong if you did 49 here on the exam. We understand that we're all human and we see things a little differently. So, but in this case, we said it would be what? Did we say 50%? Lost my train of thought there. Okay, 50% middle area. So what do the two tails got to be then? 25% here, 25% here. Again, all of our work is done, just interpreting the data. So always go back to the question. They're concerned with the chance that the sum would be greater than 120. So 120 was a z-score of 0.67, so greater than this point. So what is the area that's greater than that? 25%. So we would say there's a 25% chance that the sum of the 36 draws will be greater than 120. There's the big conclusion. Does that make sense? Great. So let's move on. You'd expect the average of the 36 draws to be blank, give or take blank. So again, we got our expected value and our standard error that we need to fill in. So now we need to do this with the expected value of the average. And what's the expected value of the average? What's the formula there? No formula, right? Same thing as percent, no formula. The average of our box is going to be the same average of our sample, right? Whatever we're pulling out of that box, take the average of our sample, we expect it is going to reflect the box that it came from. So no formula there. So the expected value of the average is equal to the average of the box. And what was the average of this box? 3. So we would expect the average of the 36 draws to be 3, because the average of our box is also 3, right? See where that's coming from? Okay, give or take, so now we're going into standard error. Got our wiggle room here. And so we need to do the standard error of the average, right? Which is the standard deviation divided by the square root of n. Okay? So our standard deviation we already calculated to be 3, square root of n, square root of 36 draws. So 3 over 6 is 1/2, so about 0.5, right? Same thing as 0.5. So we would expect the average of our draws to be 3, give or take about 0.5, our standard error. Everybody good there? All right, good. Okay, so the chance that the average of the draws will be less than 4. Okay, so 4 is our number of interest, right? That's our value of interest. We're concerned about the chance of getting less than 4. So step 1, always go to a z-score. When in doubt, go to a z-score. Value minus expected value over standard error. Probably sick of hearing me say that by now. Okay, so our value of interest is 4. And we expected the average to be 3. And what was our error? Our little area of error is 0.5. So that's going to be 1 over 0.5, which is 2. So there's our z-score. Got a z-score of 2. So let's go to our normal curve. There's 0, 1, 2. Okay, this is a small little curve over here. Okay, so there's 2. Anytime you mark one z-score, you always have to mark its opposite. 95% is between them, which means we have tails of 2.5. We've seen that curve about 50 times in this class so far. Okay, so which part of the curve are we interested in? Less than 4, right? And our z-score for 4 was 2. So we're interested in all of the area that's below 4. So not just that middle area, the whole thing, all the way down. Okay, so what's the probability of getting less than 4? We're going to say that's 95% plus 2.5%. So we have a 97.5% chance of getting an average less than 4 on 36 draws. And that makes sense, right? I mean, the average of the box was 3. So we really are going to expect that average to be 3. And the standard error is 0.5. So I mean, it does make sense that if the average of your box is 3, you're going to expect almost all of the time for your average to be less than 4, right? So that's good. Always just try and step back and think about it intuitively, logically. Okay, thumbs up if we're all right. Okay, that's a lot. That's a good number of thumbs. All right. Okay, so you'd expect the percentage of the 2. So same thing, now we're working with percentages. So you'd expect the percentage of the 2s to be blank, give or take blank. So first thing, we need to find our expected value of our percent. So the expected value of the percent, remember there's no formula, right? It is just the percentage of 2's in the box. Well, let's go back up to our box. What percentage of 2's are in the box? What percentage of the tickets are 2's? We've got 2 tickets that are 2's out of 4 tickets, which is 1/2, which is 50%. So we'd expect 50% of our tickets to be 2's. Give or take blank. Okay? So now remember, to find the standard error for the percentage of 2's, we need to first change to a 0, 1 box. Because now, like imagine pulling from a box. We're concerned with the percentage of 2's. Let's say we get a 2 the first time, hooray. We get a 0 the second time, aw rats. We get an 8 the third time, aw rats again. But was there really any difference between pulling a 0 and an 8? No, they're both not 2's. So it doesn't matter if your ticket says 1, 3, or 3,000. If it's not a 2, it's not a 2. So that's why we're going to convert to this 1, 0 box. So our new box is going to contain, we'll call them 2's, and we'll call them not 2's. You able to see that all right? Okay, so 2's and not 2's. And so what should we write as the value of these tickets? If we're summing up the percentage of 2's, if we're summing up the number of 2's that we get, every time we get a 2, we're going to say hip hip hooray, there's 1 2, there's 2 2's, 3 2's, 4 2's. So we're just summing them up, so then we're going to put 1 as our value of 2. And anything that's not a 2, you just skip over and keep counting when you get another 2. So we're going to say 1's and 0's. And we have 2 of each, right? We got 2 2's and 2 not 2's. Does that make sense? So there's our new box. Everyone understand why we had to convert to a new box? We're concerned in purely the percentage of 2's. So we needed to fix that box and get rid of the 0 and the 8, because it doesn't matter that they're a 0 and 8, it just matters that they're not a 2. Okay, so now back to our standard error of the percentage. That is going to be what? Standard error of the percentage is the standard deviation divided by the square root of n times 100. So now calculate our standard deviation. Is our standard deviation still 3 as it was above? No. New box, new standard deviation. That's the rule. New box, new average, new standard deviation. So our standard deviation for this box, luckily, is going to be easier to calculate than this whole mess that we were just working on earlier. This is going to be easier. It's going to be what's written on the tickets. So we have 1's and 0's on our tickets times the square root. Let's see, we've got 4 tickets total. 2 out of the 4 say 1, 2 out of the 4 say 2. So the standard deviation of this box is going to be 0.5, right? Okay, so 1/2 is our standard deviation. So then back over here, our standard error is 0.5 divided by the square root, running out of room, of 36 times 100%. And so that's going to get us 8.3%. So there's our standard error. So we can put that right back up over here, 8.3%, which is our standard error. So we'd expect to see 50% 2's, give or take about 8.3%. Okay, so now moving on, what is the chance of getting that the percentage of 2's would be more than 60%? Okay? So more than 60%. So 60% is this value of interest. So our z-score, again, is going to be value minus expected value over standard error. Value of interest, we just said, was 60%. We expected to see 50% 2's divided by our error of 8.3%. And that's going to get us 10 over 8.3, which is around 1.2. So there is our z-score. So let's hit the normal curve now. There's 0, 1, 2, 3, the other way. So let's plot our z-score, 1.2, that's like right there. So I'll say 1.2, there you are. And what's the rule? You plot one, got to plot the other. Negative 1.2. Okay, and the area between those is going to be what? Another one we don't have memorized, right? So let's hit the curve, or the chart, the graph in the back. So a z-score of 1.2, there we go, nice and easy one. 76.99. Let's call it 77, folks. All right. Oh, great, I lost my place. Oh, there we are, okay. World's not ending. Okay, so we have 77% as our middle area between the z-score of -1 and -1.2 and +1.2. So 100 minus 77 divided two ways is going to get us 11.5% here and 11.5% here. So back to our question. We have all the information in front of us. What's the probability that the percentage of 2's will be more than 60%? Well, more than this z-score right here, right? So the area beyond our z-score of 1.2. So 11.5%. So we're going to say that 11.5% chance of getting more than 60% 2's on 36 draws. So there's the conclusion. So now this has been, you know, where we're talking about this ticket, this box with tickets of 0, 2, 2, and 8. How's that going to help you next spring break, right? So let's enter the world of gambling. My sister's on her honeymoon right now, and on their way back they're going to hit Vegas for next weekend so that my new brother-in-law can go blow all their wedding money on March Madness gambling. And she asked me, you know, what's the safest game to play? And I would say, if I were going to go to Vegas, I would do roulette. I think that's where your best chance is. So let's take a look at roulette. It's probably the least exciting, but probably the one that you'd walk away, you're not kicking yourself for. Not the one you win the most money for either. So if you're one of those big risk takers, don't go for roulette. But for those safe people who are just looking to have an evening in Vegas. Okay, so you play roulette 100 times, betting $1 on red each time. So what's the chance that you win more than $1? So for the non-gamblers out there, when you're betting $1 on red, what that means is that if this roulette wheel, if the ball lands on one of the red slots, so if it lands on red, we win $1. Hooray! All right, and if it lands anywhere else, black or green, we are going to lose $1. Not happy. Okay, so let's make our box based on this knowledge. So anytime you sit down at a table in Vegas, there's always two outcomes. You can win or you can lose, right? So let's talk about winning first. If we win, what do we win? What's the stake here? $1. So we're going to say when you win, you have a value of 1 on that ticket. When you lose, what's at stake? What's our risk here? -1. We could also lose $1. Now, how many ways are there to win? Remember, there are 38 tickets, right? There's 38 slots on a roulette wheel. 18 red, 18 black, and 2 green. 2 green. So if we're betting on red, there are going to be 18 red slots. So 18 ways we can win. And ways we can lose, 20 for those 18 black and 2 green. Okay? So let's take some statistics on this box. What is the average of this box? The average of this box is, well, we have 18 tickets that say 1 plus 20 tickets that say -1 divided by 38 total tickets in our box. So that's going to be -2 over 38, which is -0.0526. So if you sit down at a table and play one game of roulette, you can expect to lose about a nickel, which is pretty good for, I mean, you're playing for the entertainment, right? So, okay, so then let's talk about our standard deviation. Standard deviation is going to be what's written on the tickets minus each other. So 1 minus -1, the absolute value though. So 1 minus -1 is going to be 2, right? Times the square root of, well, we've got 38 tickets, right? And 18 of them are winners and 20 of them are losers. So we're going to get 2 times, and we throw that into our calculator. Let's see now. Throw this into our calculator. See if you can see this at all. Okay, so the square root of 18 divided by 38 times 20 over 38. And that's about, let's call it, it says 0.49999. Let's just call it 0.5. So 2 times 0.5 is 1. So there's our standard deviation. So now we have our box, we've got our average, we've got our standard deviation. Let's jump right into this problem then. So the probability that we win more than $1, we walk away a richer person, we win more than $1. Okay, so our first thing we always need to do is get our expected value. The expected value of the sum, because we're summing up the total number of money we walk away with. And that's going to be n times our average. Well, how many times are we playing? 100 times, so there's our n. And the average of our box, we said, was going to be minus a nickel, right? So times negative 0.0526. So that is negative $5.26. So you can see why Vegas stays in business, right? Everybody's losing $5 every time they play 100 times. All right, and then standard error of the sum is going to be the SD times the square root of n. And our standard deviation of the box we said was 1, and we're going to play 100 times, so that's $10. And now you can see why people keep going back to Vegas, because you can expect to lose $5, but this wiggle room of $10 entices people to go, and they think, oh yeah, it's going to be me, I'm going to be the big winner. Just one more roll. I'm hot, you know? Okay, so our z-score. Z-score is value minus the expected value over the standard error. So our value of interest, the amount that we're concerned with winning, is $1. We're concerned with winning more than $1. So we're gonna, our value is $1 minus our expected value, and our expected value was negative $5.26, divided by our standard error, which was $10. And that gives us a z-score of about 0.626, right? So there is our z-score. That's the most important part, right? So now we have our z-score. Let's hit the curve, all right? We've got 0, 1, 2, 3, negative 1, negative 2, negative 3. So 0.626, it's going to be right around here. 0.626. And anytime you plot 1, you've always got to plot the opposite z-score. So negative 0.626. And the area between those two numbers, those two z-scores, back of the book. So 0.626. Again, we're in between these two z-scores, right? So in an exam situation, what would we do? Well, we got 0.6. We got 0.65. It's going to be in between those, so it's got to be between these two areas, 45% and 48%. So let's call it 46. Does that sound good? We would accept 47. So 46% middle area. So 46% middle area between these two z-scores. So 100 minus the 46, split both ways, it's going to give us 27% over here, 27% over here. So all the work is done for us now. Now it's analyzing. We sit down at that table, we play 100 times. The likelihood of us winning more than $1, well, here's our z-score for $1. Likelihood of winning more than $1 is 27%. Because we're concerned with the area greater than that $1 mark. So we have a 27% chance of winning more than $1 on 100 plays. Would you take those odds? What do you guys think? I'd probably play. That's not terrible, especially for Vegas. Everything's tilted towards the house. Okay, so you play roulette 900 times. Okay, so this guy just could not walk away. He played 900 times, betting $1 on red each time. So what's the chance that you win more than $1? So what are the rules here? If we win $1, or if we win $1. If we lose $1. So same rules as above. And anytime the rules are the same, your box is going to be the same. Same rules, same box. Okay? So what does our box look like then? Just to reiterate, we had 38 tickets total. Winning tickets, there were 18. Losing tickets, there were 20 to get us 38 tickets total. Okay, and that represents winning, that represents losing. Okay, and we said that the average of this box was negative 0.0526, and the standard deviation of the box was 1. So now let's say, what's the chance of winning more than $1? So our value of interest is $1. So first let's figure out our expected value, how much we can expect to win or lose sitting down. So expected value of the sum of all of those dollars that we're either winning or losing is n times the average. Well, how many times are we playing? 900 times. And the average of our box we said was minus a nickel. Okay, so that is going to get us negative $47.34. So you can expect to be walking away $47.34 poorer after playing 900 times. Okay, but let's take a look at that standard error. Standard error of the sum is SD times the square root of n, which gets us 1 times the square root of 900. So 1 times square root of 900 is 30. So we're going to say $30, give or take $30. So now to our z-score. Our z-score is the value minus the expected value over the standard error. Our value of interest is winning more than $1. So our value is 1. Our expected value is, where did we say? Here it is right here. Our expected value is losing $47.34 divided by our standard error of 30. So that is going to get us 1.61 as our z-score, which is the most important part of this whole story. So our z-score is 1.61. So now to our normal curve. 0, 1, 2, 3. Negative 1, negative 2, negative 3. So 1.61, let's call that right here. Always have to draw its opposite. So there's 1.61, there's negative 1.61. Okay, and the area between 1.61 and negative 1.61 is going to be 1.61. Let's see. So there's 1.6, 89. Oh, what do you guys say? 89.2, I'd say. That'd be my best bet. Again, everybody has their own way of thinking about it. We would accept 89.3, 89.1. 89.2% middle area between those two. So 100 minus 89.2 divided by 2 is going to get us 5.4% on the left tail, 5.4% on the right tail. All the information's there. It's a matter of interpreting. So our z-score is 1.61. We're concerned with getting more than that amount. So what do we see? 5.4%. So on 900 plays, we have a 5.4% chance of winning more than $1, which I would say frowny face, right? The guy should have stopped at 100. So there you go for all gambling addictions out there. Better to walk away. So now this last page, let's take a look at this. This is a technical point that she's putting in there. So far we've been talking about the probability of getting more than this amount, less than this amount, or between these two amounts, right? Well, what about just winning $1 exactly on the money? What's the chance of walking away with just $1? Not more than $1, less than $1, or between $1 and $2. We're talking about the probability of getting this exact amount. How do we do this? And the way that this is going to work, and I'm just going to go through this briefly. So the chance of getting 50 heads, exactly 50 heads, not less than 50 heads, more than 50 heads, between 45 and 55, what we've been doing so far, we want to know, getting right on the money, 50 heads exactly. Well, what's the range of numbers that we would round to 50 for? We would round to 50 for 49.5 and we would round to 50 for 50.4, right? That's the range that we would consider 50, right? Anything above or below that is no longer 50. So that's our range for 50. So basically what we're doing here is you would convert these to z-scores, and then you would plot those z-scores very tightly right next to each other. There would be a very, 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 very skinny area between the two. And that would be your probability for getting exactly that. This is just a technical point. It will not be covered on the exam. And this page, I think, is allowed to be blank if you want to do the bonus work. So we can say, not on exam. Leave blank for bonus. Okay, so let's just hit up this chapter review summary. Everybody see that? Got what you needed here? Just a technical point. Okay, so the first few points we had already hit with Professor Fireman's central limit theorem. And here, down here was the moral of my lecture right here. That's the take-home point. I hope you guys learned something today. It was a lot of fun working with you. If you have any questions, anything you'd like to clear up, come on down and see me. Stop by my office hours. We're in the office every single day from 3 till 6 o'clock in Illini Hall. Thank you very much. Have a great day, everyone.